Hello, welcome to this third lecture of week 7. We will continue our discussion with some more examples about the problems which we have dealt in this particular week, and some associated problems also. So the first example we are looking into is from the positional astronomy. We have a source which is RA is 12 hour 30 minutes and declination is 0. So alpha is 12 hour 30 minutes and delta is 0. Okay. So astronomers decided to check it out and set out to observe it with their own telescope, which is located at 78° west longitude and 35° north. So the lat is 35° north and the longitude is 75° west. They first check their computer and see that the current LST at the telescope is 3 hours of LST. So LST is also given, is equal to 3 hours. Okay, so what are the RA and the deck of the astronomer's zenith? Okay. So the RA of the zenith is given by the LST because we have known that at the zenith our angle equal to 0. So RA is equal to LST. So then LST is 3 hours, so RA becomes 3 hours. And declination is what? Declination is the local latitude, which is 35° north, right? Yeah. So declination is also 35°, plus 35°. The next question is, what is the current hour angle of the radio source? That's an interesting point. The current hour angle, how can it be figured out? The hour angle is equal to LST minus the RA. Okay. Now, did we get anything about the RA? The RA of the source is 12 hour 30 minutes, and the LST is 3 hours. So the hour angle is then 3 hours, which is the LST minus the RA. This is given by this, but note that this is minus 9 hours. So that means the source is still 9 hours or so away from the transit. So this is so far away from next transit. Okay. What is the third question? The third question is the radio source above or below the horizon at this time? So we determine the altitude. We calculate the altitude of the source. So this may be some mismatch. So altitude is calculated as because 35° is the zenith. So the altitude of the source is 55°. That's the altitude of the particular source. Okay. So it's when it at the transit, we can say that the transit, the source is definitely can be will be above the horizon. Example number 2, we calculate the radio telescope has a collecting area of 1.2 meter square to observe a radio source at a frequency of 1420.4 megahertz with a bandwidth of 2 megahertz. You measure a detected power of 1.2 times 10 to the power minus 22. What is the flux density of the source observed? It's kind of a bit of going backward, and try to again explain if you have any further problem. So this links with the source flux density with the power, the effective area, and the bandwidth. So they are linked in this manner. Okay? And so if you simply substitute all the values, you will get the final answer. So we decided we will go back a little bit and again go forward. And so every week from now, we will go back to some old concepts as well. Example 3, the data from a radio telescope that can detect both left circular and right circular polarization. This is a typo for left and right circular polarizations at the same time are processed through a program that calculates Stokes parameter. The results indicate that I, the Stokes I parameter, is given by 0.5 Jansky per beam, and Q is 3 millijansky per beam, U is 4 millijansky per beam, and V is 0. Does this radiation have a non-zero polarization? If so, what kind of polarization does it have? Characterize the polarization. The radiation is unpolarized only if Q, U, and V are equal to 0. Since Q and U are non-zero, the radiation is polarized. Q and U are measures of the linear polarization, while V is a measure of circular polarization. Since V is equal to 0 and Q and U are not 0, the radiation is linearly polarized. The percent polarization of linear polarization is given by L over I, where L is the quadrature addition of Q square plus U square and square root of that. So if you do that, you figure out that the percentage linear polarization is given by 1%. The position angle can be given by theta is equal to half tan inverse of this value. So Q over U, U over Q, and it is given by 63.4 degree. Okay, so that's you get. Next example, a pair of antennas are aligned in the east-west direction to be used as an interferometer with a fixed baseline B. Antennas are pointing at a particular source, doesn't matter. The alpha is given, the array is given by this, 8 hours, 54 minutes and 48.86 seconds. And delta is given by plus 20 degrees, 6 minutes and 30.6 seconds, according to the J2000 epoch. At the time of observation, OJ287 is an hour angle of 2 hours plus 2 hours. Observing at a wavelength of 1.25 centimeters, we obtain a cross correlation and find the rate of change of phase to be equal to minus 0.432 radians per second. We can use this data to measure the baseline length. What length do we infer? Okay. So we use this standard formula of using the fringe rate, and we can just substitute the values we know. If we substitute the values, we know what is the delta. So delta we know. which is equal to plus 20 this thing, 0630.6. So delta is 20 degree 630.6, so 6 minutes 30.6 arc seconds. That is given. We know the baseline. We do not know the baseline. We know the lambda. Lambda is given by 1.35 centimeters. Okay. And fine, since the baseline is purely this thing, g equal to 0, that is okay. Time is 2 hours, that is 7,200 seconds. For the declination, we convert the arc seconds into fraction of a degree. So we converted the entire thing into delta equal to 20.1085 degree. The product of omega E times time is given, gives you 0.5256, which can be expressed as 30.1 degree. Okay. So 0.432 is radians per second. You know how many seconds has evolved, so you can put that in. So finally the B comes out to be the, so if you put all the values together, you finally get the baseline length given by 15.65 meter. So that's how you derive the baseline length. Okay. The next question is, after the baseline is measured, we use this interferometer to observe a new source with coordinates alpha given as 13 hour 24 minutes 12.909 seconds and A delta is plus 48 degree 48 minutes and 11.8 seconds. The measured fringe frequency is given by this. So what was the hour angle which we observed this new source? So then you have the value A and B, B and solve for T. So this is the in terms of degree. You have the degree also, delta is converted into from degree minute and second into degree. Since the fringe frequency is positive, the source is still approaching transit. That is also known. We then get the cosine T value is given over here, and we can calculate the omega F from there, and then the T. That gives us 10,300 seconds. So since it is approaching the transit, so it is still 2.87 hours before the transit. So transit will happen 2.87 hours after now. Okay. So that's what you can do. So basically, you simply have the fringe frequency is related with the baseline and lambda, and the delta of the source, so that we have just substituted, and we have got this particular problem solved. The submillimeter array in Hawaii is composed of, next example, submillimeter array in Hawaii is composed of 8 dishes of 6 meter diameter each, while the very large array in New Mexico has 27 dishes of 25 meter diameters each. Which array would benefit from more from the addition of another dish? So the SMA has interesting problem. SMA has 8 into 7, 28 baselines. With one more antenna, it will have 8 additional baseline. So 36. This is an increase of 29%. VLA has 351 baseline. If you add one more, that will be increased to 78, which is a 7.7% increase. So definitely with a larger array, if you just add one to the smaller array, which is the SMA, that will benefit much more than the VLA. So by definition, if you add one more dish to the smaller array means an array which is smaller number of antenna, the percentage increase in the baseline will be much more. Next example, if a radio interferometer facility contains 25 antennas of 40-meter dish operating at 21 centimeter wavelength with 95% efficiency and having minimum baseline of 500 meters and maximum baseline of 35 kilometers, then what is the resolution of the facility in arc seconds? What is the field of view in degrees and total collecting area of the interferometer in square meter? So resolution is lambda by the maximum baseline. This B is nothing but the maximum baseline in an interferometer. So if you convert them, you get 1.24 arc seconds. Field of view is still remains close to the individual antenna. So it links with the D, which is the diameter of the antenna of each antenna. So it remains 18.05 arc minute. At yes, at a frequency at a 40-meter dishes, 21 centimeter. Yeah, this is what it is. Total collecting area is given by area A total of 25 antenna. This is the efficiency pi d by 2 whole square. So if you put all the values, you simply get to this calculation. Pretty simple by now. We have done more examples on this kind of things. Example number 7. Consider you are located at a latitude of 22 degree 7196 degree north and longitude 75.8577 degree east. If you are trying to observe a source with RA of 12 hour 10 minute 15.3 seconds and declination of 22 degree 43 minute 10.56 seconds, then what is the correct rise and set time of the source in LST? So the LST is so 6 hour is the so essentially the declination is almost equal to the latitude of the observer, more or less. So you have a declination equal to the latitude. So declination of the source is around 22 degree 43 minutes, and which is very close to this 22.7196 degree north. Okay, so the source will pass through the zenith. That means the source is equally up and equally down. So in a day you have 24 hours, If it is equally up, meaning the up time is about 12 hours and down time is also 12 hours. That means it is not visible for 12 hours and is visible for 12 hours. So the RA minus 6 hours is, so we want to know is the rise and set time in LST. Now remember, when it transits, when it is crossing the zenith, the hour angle is equal to 0 at the transit. So at the transit, the RA is equal to the LST. So the LST of the rise is 6 hours before and LST of the set is 6 hours after the RA. So you simply just subtract 6 hours to calculate the RA in LST. That is 6 hours, 10 minutes, 15.3 seconds, and set is 6 hours after the RA, and that is 18 hours, 10 minutes, and 15.3 seconds. So these calculations are very, very powerful. If you simply remember that that diagram we did, where you have an observer and you connect the north and the south pole. So if you're connecting to the north and the south, so you draw the, and the zenith is here, so you draw the imaginary great circle, and this is passing through your zenith. So any source which is passing through the zenith will be, delta will be equal to your latitude of the place, and so you can calculate the rest remaining of this. And at any transit, the hour angle is 0 at transit. So HA equal to 0 and RE is equal to the LST. So with that, you can calculate a lot of different things. Let's take up another example in this same method. A cosmic source is located at a latitude, galactic latitude of plus 8 degree 32 minute 48.63 seconds and galactic longitude of minus 71 degree 12 minutes and 40.4 seconds. Find the position to the equatorial coordinate system. If you follow the coordinate transformation given in the lecture notes, you just simply put the values and you will finally find that alpha and delta in an epoch of 1950 is given by this. So it's simply substituting the values, and we haven't derived it. It's a bit cumbersome and we will stay away from it because it's just an introductory course in radio astronomy. Thanks. What is the far field distance of the Green Bank telescope? Green Bank telescope is for diameter of 100 meters, and if you're observing at 21 centimeter lambda, then we know that there was this few things, right? There was when you have a radiating dipole, we have 3 different zones. We have first zone, which is the near reactive one. We have the second zone, intermediate zone, which is the Fresnel zone. And we have the third zone, which is the far field, or we also call it Fraunhofer zone. This boundary between the near Fresnel zone and Fraunhofer zone is marked as 2d square over lambda. So the d is the dimension, so that 100 meter is the d. So d equals to 100, sorry, it's not b, it's d. So d equal to 100 meter and lambda is also equal to 21 centimeters. So if you put that, you find out that this boundary is 95.24. So any r which is greater than 95.24 defines the far field. Kilometers, of course. Yeah. thank you. I hope that you got benefited from this discussion of this additional examples. We particularly trying to incorporate more and more additional examples and going through them tenuously, just to help you understand different concepts. We are not only restricting this to the existing week's lectures, but also we are extending them to the previous week's lectures as well. For your help, we have also going to start this week. Our next two lectures will be on Introduction to Python. We plan to introduce Python and show you some examples on how Python can be used for demonstrating Fourier transforms, for example, for some radiation patterns, for example. And it's a very good tool, and you need to have the expertise with you, whether you're from science or engineering. So it's at a different outset, having a Python expertise is always useful. But for the context of this particular course, we will introduce Python this week, and we will utilize the Python's different routines to show you the demonstration of Fourier transform, convolution, and also a little bit of radiation patterns of very simple radiating bodies. Hope you've liked our lectures. So stay tuned for the next lecture. Thanks for joining me today. Thank you.